Welcome to this video on PCB design for EMI and signal integrity. In this video, we're going to be looking at the basic principles and ways you should route and lay out your PCBs to minimize chances of EMI failure and to maintain proper signal integrity. In future videos, we'll be examining this EM test board, which was made by JLCPCB and designed in Altium Designer, which shows some things you should and shouldn't do when it comes to EMI and signal integrity of a printed circuit board. I'm very pleased to say that Dr. Min Zhang of Mach 1 Design will be helping out with analyzing the EMC characteristics of this board. Thank you very much for Altium for sponsoring this video. The boards you see in my channel are predominantly now made with Altium Designer, and I'll use Altium Designer for pretty much all of my work and all of my complex designs. If you'd like to give Altium Designer a try for yourself, you can go to altium.com/yt/philslab to get yourself a free trial. The EMI test board you saw at the beginning of this video was also indeed made with Altium Designer. As usual, thank you also very much to JLCPCB for sponsoring this video. The EMI test board you saw at the beginning of this video was manufactured and assembled by them. If you'd like to get this board manufactured by them as well, you can go to my GitHub repository, github.com/pms67, and look for the EMI test board repository, where you'll find the firmware as well as the hardware for Altium Designer. As always, I highly recommend you watching the Rick Hartley video on grounding, which is on the Altium YouTube channel. This is the video here, and it's 2 hours long, but well worth the watch. I'll leave a link to this in the description below. The core takeaways, and what most people don't realize when it comes to electronics and PCB design, is that the electric and magnetic fields contain all energy. Most people think energy travels in the copper, for example, the signal trace or return plane, but in fact it does not. The signal energy, or rather the fields, travel in the dielectric space between the trace, which might be the forward trace, and some sort of return plane. The forward and return paths, so the planes or traces, must be well defined at all times to maintain proper signal integrity in EMI. In essence, the copper, consisting of the forward and return paths, are simply a waveguide for the fields. Here's a nice illustration of the electric and magnetic fields as seen for Microstrip and Stripline, and these images are courtesy of Rick Hartley. On the left we can see a microstrip trace, so not a buried trace. We have essentially air as our first dielectric and then the dielectric of the PCB underneath. You can see there's quite a lot of field spread for both the electric, which is in blue, and the magnetic fields in red. You can already see on the right side, this strip line, that the fields are better contained because we have reference planes at the top and below the trace in the middle. So all the fields like to attach to these return or reference planes are now better contained. And thinking about electric and magnetic fields like this, rather than electron flow in coppers, really helps when designing PCBs and containing fields, which is basically what this is all about. Another misconception is when it comes to frequencies in the digital domain. For example, many people assume that the clock frequency of a signal or microcontroller, for example, the highest clock frequency in someone's system, is the highest frequency of concern in a system, and this couldn't be further from the truth. Typically these days we are in the digital domain, and when we rely on pretty much square waves to transmit data. Of course, these won't be ideal, but close to, hopefully. The fundamental of these square waves may be the clock frequency, at 8 or 16 megahertz. However, we don't need to just be concerned with this fundamental clock period as indicated in this diagram. We also need to be concerned with the transitions. So for example, this rising edge and the falling edge. And this is actually where the bulk of the signal energy and the frequency content is contained, rather than this fundamental clock period. The highest frequency of concern, given these rising and falling edges, can be determined via the Fourier series of a square wave, for example. Typically we don't go to that much effort, and we can derive a simple approximation to give us the signal bandwidth in gigahertz is 0.5 divided by either the rise or the fall time, depending on which is the fastest, in nanoseconds. So this is all well and good, just doing 0.5 divided by the rise or fall time in nanoseconds, and that's a very simple approximation. But the question is, how do we even figure out these rise and fall times? Usually from datasheets it isn't entirely evident, and usually that just gives us the best case. We start getting problems when we try to find these rise and fall times from manufacturer datasheets. So for example, I take this fairly generic STM32 G series microcontroller. It's typically clocked at 64 megahertz, has various peripherals and so forth. If I go to the datasheet, which I've downloaded here, and then look for rise time, you can see we have various speed settings of the microcontroller. We have these output rise and fall times for specific I/O voltages and capacitive loads on the lines. The problem with these output rise and fall times is that they only give us a maximum, so essentially a best case scenario. So the output rise and fall time for this particular GPIO could be 100 nanoseconds, but they don't give us a minimum. The minimum could be, for example, a picosecond, just to make an extreme example, which would mean our bandwidth is incredibly high.
100 nanoseconds doesn't really tell us very much. It gives us, the best case, but we should never design for the best case. We should always design for the worst case. So how do we get around this limitation? The nice thing is, most manufacturers, if not all, should provide IBIS files, or IBIS files. If we go to CAD resources, for example, then go down to the bottom, we can download an IBIS model. And these are used for simulation, and you can extract rise and fall times from these models. Another very popular microcontroller, and one we'll look at the IBIS file for, is the ATmega328P. And this is a microcontroller you will typically find on these Arduino Nano boards, I believe they're called. A very slow internal speed, as we'll see. It's 32 megahertz, and these 80 megas often go down to 8 megahertz or something like that. If we scroll down to the bottom of the page, there's also an IBIS model, which I've already downloaded. Once you open the IBIS model, you can see there's quite a lot of stuff to this, and this is great when you're running simulations, when you need to extract specific information. What we want to look for, and we can just search, is for this ramp section. So I can click on Find Next, and you can see this section has to do with, for example, some sort of GPIO pad. It'll tell us the tests for capacitive load, what the logic low and high thresholds are, and so on. But for rise and fall times, we want to scroll down and look at the ramp section. In this ramp section, we'll find dV by dt R and dV by dt F, and you've already guessed it, this is for rise and for fall times. However, the IBIS model specifications tell us this is a rise and fall time from 20% to 80%, whereas our traditional definition of rise and fall time are from 10% to 90%. So we need to scale these values to go from 20 to 80% to 10 to 90%. Keep in mind, this is for specific loading. This is typically for the 50 ohm load connected, and your system, of course, may be different, so take these with a slight pinch of salt, but they are the best thing we have from these IBIS files. So they'll give us the voltage range this signal travels through, divided by the rise or the fall times, typically in nanoseconds. In the ramp section, we then want to look at the max, and that's either rise or fall time. So we want to take the absolute worst case, and this seems to be the full time at 0.76 nanoseconds. And remember, this is from 20 to 80%. So given that we've now looked at an IBIS model and seen how to extract the dV by dt data, or rather the rise and fall time data, the question is, when do we have to care? Remember from our example IBIS model, our dV by dt, which was defined as a 20% to 80% rise or fall time, was 0.76 nanoseconds. Now we have to convert that to be able to use our formula into a 10 to 90% rise on fall time. So all we have to do is scale it linearly, and that gives us a 1 nanosecond fastest edge or fall time. Therefore, using 0.5 divided by rise or fall time in nanoseconds, so 0.5 divided by 1 nanosecond in this example, gives us a 500 megahertz maximum frequency we have to be concerned with. And this is pretty crazy because most people would assume, this is a slow 32 megahertz MCU, but rather all of the frequency content is hidden, so to speak, in these rising and falling edges. So it turns out we actually need to take care when our traces, so our trace lengths, start to look like distributed elements rather than lumped elements. This means that the trace length starts to be comparable to the wavelength of the highest frequency component. So if our trace length is similar to the wavelength in this example of a 500 megahertz signal, then we have to be concerned. Before we get to traces, let's briefly talk about how we control EMI and signal integrity from the slides and information we just saw. The main idea is to simply contain fields. We saw that all of the energy is stored in the fields between the dielectric or in the dielectric space. So this is our main job as PCB design engineers. Another thing we can do is choose ICs that can do the job we need them to do with the slowest rise and fall times possible, because slower rise and fall times mean less energy and a smaller bandwidth. We want to keep our high energy frequency traces as short as possible, and we want to improve power delivery by minimizing inductance, decoupling, and so on. This is just a brief overview, but let's go through some aspects in more detail. And keep in mind, this isn't an extensive discussion in this short video. One of the most important parts of PCB design and controlling EMI and signal integrity is the Stackup. I already have a fairly detailed Stackup and build-up video on my channel, and this is the one I'm talking about here. It's number 56 on my channel, and I'll leave a link as usual in the description below. The first point is to use thin dielectrics between signal and reference planes. For example, you can see this 4-layer stack on the right. We have a signal layer, then a prepreg or dielectric material layer, and then a reference layer underneath. We want this prepreg layer to be as thin as possible because this improves the coupling, reduces inductances because we get smaller loop areas, and if we have power and ground planes adjacent with a thin dielectric, this of course increases the interplanar capacitance, improves power delivery, and so on. Going, for example, to the JLCPCB manufacturer's website, we can go to their control impedance PCB layer Stackup,
and then scroll down because they have several different stackups. One is this JLC7628 stackup, and one is this 2313 stackup. Now they look fairly similar. The core is thinner here, but the good thing about the second JLC2313 stackup is these thin prepregs between top layer and the inner layer next to it. So in preference, I would usually go with this JLC2313 stackup, for example, and this will depend on your PCB manufacturer of choice. This has all of the performance benefits we just talked about. If you're designing your own stackup, then of course try to keep this in mind. This is also a reason why with my 4-layer stackups, I usually just route power if I can, and for most low speed or low frequency designs, this is more than fine. In this way, I have layer 2 and layer 3, my internal planes, both as ground planes. Because I get better coupling between the signals, I have better references for my signal layers. In addition, if I have a ground and power plane, for example on layer 2 and layer 3, I have this very, very thick core material in between, and this gives me absolutely no advantages because this core material is so thick. Additionally, I want at least one ground layer adjacent to every signal and power plane. Again, we want to contain fields, we want to reduce our inductance, we want to provide good return paths and improve the power distribution. Typically, for high-speed signals, for very high-speed signals, I'll route them as stripline, so on my internal layers, and that'll be typically on higher layer boards, 6, 8, 10, and so forth. In addition, avoid placing signal layers next to each other. If we have signal layers next to each other, remember fields will cross-couple, we'll get crosstalk noise, and so forth. For example, this zinc board with DDR memory, loads of high-speed interfaces, gigabit Ethernet, and so forth I'm working on. This will be a 10-layer board. So if I go to Altium Designer and go to my layer stack manager, you can see the stackup, or at least the preliminary stackup I've gone with. And hopefully you can see the rules I always go with. So I'll have signal layers on the outer, and then always a ground adjacent to every signal and power plane. So I have signal, ground, power, which is then adjacent to a ground, signal and power, ground, signal. So always one ground at least adjacent to every signal or power plane. Coming back to traces and also looking at termination, remember we want to keep our traces as short as possible. We want to keep them short because we want to keep the traces as lumped elements. We don't want them to be distributed elements. We have to take care of, okay, how long can these be before we start getting signal integrity or EMI problems. Now, them being counted as lumped depends on the inner or outer layer routing. This is because waves propagate at different speeds in different dielectric materials. This is an incredibly important formula, and I'd encourage you to remember this, and this gives us the critical length. So for a given rise or fall time and a given dielectric constant, when do we have to care about the trace length? And this is a quarter of the rise or the fall time, whatever is faster, times the speed of light, divided by the square root of the dielectric constant. And we'll look at this in just a second, what some typical numbers are. Another tip is to avoid traces near the edge of the PCB or near the edge of reference planes. And this is because field energy or the fields spread out between the forward path and the return path and aren't directly contained underneath the trace. A lot of times you also want to use proper termination, and there's many different termination schemes. There's series termination, parallel, and so forth. Using proper termination helps us avoid ringing, which are both SI and EMI issues and can also cause damage to ICs. Now the driver has to of course be capable of delivering this power, especially where there's, for example, a 50 ohm termination resistor and a 3.3 volt logic signal. Looking again at the trace length, here's our critical length formula. And the dielectric constant depends, of course, if we're routing on an outer layer or an inner layer trace. For an outer layer, so for a microstrip, we need to use the effective dielectric constant, and there's many calculators on the internet to help you do that. This is because we have to consider the dielectric constant of the air, or the surrounding medium, as well as the dielectric constant of the fiberglass or the prepreg. For the inner layer trace, we simply use the dielectric constant of the inner layer dielectrics. Going back to our example, we have a 1 nanosecond rise or fall time. Let's say a typical dielectric constant of 4.6, which according to a calculator on the internet gives me 3.4 as an effective dielectric constant for the microstrip. So our critical length when we start having to pay attention to our routing is already at 35 millimeters for an outer layer trace and 41 millimeters for an inner layer trace. So for a 32 MHz simple 80 mega microcontroller, we have to start paying attention at 35 millimeters. And that's not exactly a long distance. You can also see typically for a stripline trace, so an inner layer trace, 41 millimeters is longer than 35 millimeters, so it's typically usually better to route high-speed signals as stripline because you have more leeway. Looking at this EMI test board, you can see I have various different test cases set up. So a normal trace, which is then terminated, a trace as a loop. So of course, the better way to route things is to keep your trace as short as possible and don't do stuff like this where you're routing a very, very long trace. Moving on, a further point is vias and decoupling. Vias come in pairs. So normally you'll see people just place a single, for example, power via, and that's it. The way to minimize EMI, improve power delivery and so forth is to always couple vias. So keep vias close to minimize inductance. For example, if I drop a power via, I want a ground via very close or as close as possible and manufacturable as possible. In addition, when switching layers, for example, if I'm on this top layer, you can see in this image here, with my reference directly below it, and I'm using a signal via to drop down to a different signal layer, I want to place a transfer via, which is basically grounded, to maintain a good reference path while I'm transitioning along the Z-axis. Another point with vias is, if you can afford it, and if the project allows, use micro vias or blind or buried vias for better signal integrity because this reduces stubs, and this can be problematic at higher frequencies. Again, just to illustrate the point with the return via or the transfer via, here I have a trace coming out of the microcontroller, simply burying down and going on the bottom layer and up again. So this is one case. The better case to do it is have your signal trace burying down, then a ground via very close to the signal via. The signal carries on the bottom side of the PCB and up again with a ground via adjacent to it. And this improves the coupling for this 4-layer board when I'm transitioning from the top to the bottom layer and switching reference planes. Moving on to the fourth point, and that is that of reference planes. Typically, for your reference, you want solid, unbroken ground reference planes. And this is in 99.9% of the cases. Sometimes you might need to use a split ground, but usually it's a bad idea. Another point is to try and avoid using power planes or islands as references if possible. Now, of course, they can provide good references, but a lot of times, especially if you have power islands or a layer that is separated in many power planelets or islands, you have to take great care of routing directly underneath and not routing too far to the borders. The biggest point or mistake one can make with PCB design or layout is to never ever cross a split in the reference plane. So for example, if some reason you have this split in your reference plane, the worst thing you can do is cross this split with a signal trace. You always have to ask yourself, where does the return energy travel? The return path will be directly beneath the trace we saw before. Because of this split, this return path has to go all the way around. So never cross a split in a reference plane. Again, reference plane are best if they're tightly coupled, which means thin dielectrics, as we saw before. Also for 2-layer boards, if possible, you can try and make them as thin as possible. Again, this improves the coupling. Just to illustrate the point again, on the EMI test board, I've actually included deliberately a split in this return plane underneath, and we'll see with a spectrum analyzer in future videos what effect this actually has on our PCB design and the emissions. So this is something you should never ever do. The last point of this brief discussion is that of separation. Separation might be the best tool to minimize cross-coupling, crosstalk, interference, noise, and so on. Separation means either X-Y axis separation, so essentially left, right, and up, down. For example, in this picture over here, where we might have connectors on one side, digitals in its own section, a power section with switching supplies, and an analog section, far away from any digital or power section. Remember, we want to contain fields and avoid fields from spreading, and separation is one of the best ways you can do that. If you're doing double-sided assembly, of course you can use the Z-axis separation for more improvement. Additionally, the topic of connector placement is an incredibly important part of EMI, including also the filtering at the connectors and so on, but we won't go into detail in this video, I'm afraid. I haven't quite finished with the layout yet of this board, but we can already see how I've separated certain sections on this PCB. This is both an analog and digital PCB with a fairly powerful system on chip by Xilinx. We have switching regulators, and we have an analog section which is still to be laid out down here. You can see I've tried to keep adequate spacing between my digital I/O, my connectors, and this analog section over here, as well as trying to keep my switching regulators as far away as I can from my digital section, as well as specifically this analog section. I also have my analog power supplies which aren't switching on the analog end away from my switching supplies. So it's important to keep separation. So thank you very much for watching this video. I hope you learned something, and please leave your feedback in the comments. If you haven't already, please do click the like and subscribe button. I look forward to seeing you in the next video. Thank you.